afternoon, everyone. First of all, I would like to thank the organizing committee for giving me the chance to give this talk. And I'm going to take this opportunity to present my latest work, which is titled Microscale Sensing with Ensembles of Strongly Interacting Envies at High Fields. So I made this work in collaboration with Ana Martin and under the supervision of Jorge Casanova. And it was recently published, actually just yesterday, in Physical Review Research. So I'm doing my PhD in Professor Casanova's group. Here you can see a picture with some of the members in the group. And the principal investigation line of the group is the development of quantum control schemes for sensing with envy centers. Well, Ruben already introduced the envy centers. Thank you, Ruben. I don't know where you are. Okay. But, well, envy centers, nitrogen vacancy centers, are defects within the diamond lattice, which can be used as sensors, and in particular, as magnetic field sensors. So, well, this is because its photoluminescent signal changes depending on its internal spin state. And this allows to detect a magnetic field, different kind of magnetic fields, could be static or AC magnetic fields surrounding the envy itself. And well, I would like to highlight two properties of these sensors. One is that unlike other quantum sensors, they can operate at room temperature. And another important property is that they can be externally manipulated with microwave radiation. So depending on the particular microwave pattern that you apply on the envy, you will be able to measure a given magnetic signal, or, for example, you could use to detect a paramagnetic element that is close to the envy. So, in this project, we developed a particular control scheme, which is just a specific microwave radiation pattern to sense AC magnetic fields with an envy ensemble. And right here, you can see a scenario in which this protocol would be relevant. Here we have a microscale NMR sample on top of a diamond, which contains an envy ensemble. And the NMR sample is inducing an AC magnetic field on the envy ensemble. So we can detect with the envy ensemble this AC magnetic field induced by the NMR sample, and we can therefore extract chemical information of this sample. But the particularity of our protocol is that apart from enabling the detection of AC signals, simultaneously it cancels the detrimental dipole-dipole interaction among the envy centers. So what does this mean? One wants to make measurements with as many envy centers as possible, as in principle at least. But, well, this is because when you have more envy sensors, you have more detectors, so it lowers the noise floor through the statistical averaging. So this means that for the same measurement time, you achieve a better signal-to-noise ratio. But the thing is that whenever you put more and more envy centers in the diamond, these envy centers lay closer to each other, and as they have a magnetic moment, they start interacting with each other, right? And this interaction is inhomogeneous within the diamond, and it induces decoherence on the envy centers. So in this protocol, we offer the suppression of this detrimental interaction. And it allows us to use dense envy ensembles as sensors. Another source for sensitivity enhancement that our protocol uses relies on the fact that it can be used to detect signals in a wide range of target frequencies. And in this range, it's of particular interest the window corresponding to high field NMR. It's interesting to do high field NMR because at this regime, the NMR sample has a stronger thermal polarization, which means that it induces a stronger magnetic signal on the MV ensemble. So this also works to, at the end of the day, yield a better signal-to-noise ratio. So we have these two sources that our protocol allows to use for sensitivity enhancement. On the one hand, we can use dense ensembles, and on the other hand, we can use the high fields. But why are we so interested in sensitivity? Sensitivity, at the end of the day, it's one of the requirements to for the transition of the MV from the laboratory to the actual everyday life applications, right? Because sensitivity means reduced experimental time, which also means reduced experimental cost, or in general, reduced resources. So yeah, it's key for convert the MV centers or these systems as into a useful tool. And once we have this platform, it would be useful in systems where, by definition, they have a reduced volume, because these systems cannot be sensed with standard NMR approaches. This includes like microscale and nanoscale NMR, for example, for high throughput chemistry, or in material science, the 2D material characterization. Okay, so now that I have introduced and motivated the work, let me talk about the project itself. So the main protagonists are the dipole-dipole interaction among the MV centers. And this interaction has this structure right here. And as you can see, as the MV centers are packed closer together, the dipolar interaction quickly escalates because it depends inversely on the cube of the distance. So the first thing we did in this project is we studied the effect of this interaction in on a standard AC magnetic field detection scheme. This is the CPMG. So we took this setup. This is an NMR sample that induces a magnetic field on an ensemble of MVs that is interacting between them. And we computed which is the effect of this interaction on the measurement done by the CPMG. The CPMG is a fairly simple protocol, which consists on an initial and a final pi-half pulse and intermediate pi pulses. And we found out that the photoluminescent signal emitted by the MVs is proportional to this expression right here. So let me break apart this expression so we can better understand. On this term right here, we have the terms related to the target field that we want to measure. And then on this other term, it's confined the effect of dipole-dipole interactions. So we have that this term related to the dynamics of the dipole-dipole interaction achieves at maximum a value of n/2, n being the number of MVs in a particular cluster. And it actually achieves its maximum value when the dipolar interaction are negligible. Okay, so for the rest of the cases, this is when the dipolar interactions are acting, this term achieves a value in between negative n/2 and n/2. What this means is that each cluster will likely emit a weaker signal, and the different clusters on the ensemble will interfere destructively, leading to an overall signal with an amplitude penalty. So, this being the situation, what did we do? Well, we preserved the pi pulses of the CPMG protocol because on the one hand, they enable the accumulation of the signal, of the target AC signal, and on the other hand, they also provide, these pi pulses, they provide protection against slow or static magnetic noises of the surrounding. But what we did differently is we added protection in the interpulse spacing for the dipole-dipole interaction. So this protection consists on a detuned microwave driving. So imagine you apply this driving along Y, and if it's not resonant with the MV, it will have a set component. So the effective driving is not along Y, but it's a bit tilted towards Z. And one can prove that if this tilted axis forms a particular angle with the Z axis, the so-called magic angle, the dipole-dipole interaction among spin-1/2 systems is suppressed. The thing is that MV centers are not standard spin-1/2 systems. They are actually spin-1 systems, as Ruben showed us. But, well, sometimes they can be reduced to the subspace of two spin states. But the thing is that the dipolar interaction between these MVs is not exactly the same as the dipolar interaction between standard spin-1/2 systems. So, in this case, the dipolar interaction is not eliminated under this driving. We found that instead, this particular driving, what makes is it converts the dipolar interaction into a very symmetric interaction. So, in other words, whenever you are applying this particular driving on an ensemble of MV centers, the remaining dipolar interaction has this very symmetric structure. And why do we care about this? Well, on the one hand, this dipolar interaction commutes with the other dynamics that are happening, so we can separate the propagator corresponding to the dipole-dipole interactions, and more importantly, this operator, this propagator also commutes with the operator that we are measuring, which means that there is no signature of the dipolar interaction on the signal that we are measuring. So, instead of having this expression right here, which is what we achieved before, we have this other one where we always have an n/2 factor. So, this means that all clusters will emit a signal with the maximum amplitude, and also that all clusters will contribute constructively. But as some of you may have noticed, there is an extra factor, which we call the reduction factor. And it's intrinsic to the protection scheme, as it represents the part of the target signal that survives the continuous driving. But, well, here it is. So the thing is that we get to suppress the dipolar interaction, but in exchange of having an amplitude penalty. And before jumping to the results, I would like to highlight that exist alternative protocols to provide protection. This, for example, it's a bit simpler than the one I showed you before. So, and it also yields a smaller reduction. So the reduction factor is higher, but on the other hand, it is less robust against errors in the driving itself. So, well, these are the ultimate results. So on the left-hand side, you can see the amplitude of a referential MV embedded in an ensemble of MV of different densities. So we have amplitude with respect to the concentration of MVs. And here we can see that the amplitude of the signal coming from the CPMG abruptly decays as the concentration grows, while the two other alternatives of the SHIELD protocol, they decay much slower. On the right-hand side, you can see the estimated signal-to-noise ratio that we computed. And here we found that the optimal signal-to-noise ratio is achieved at 0.4 ppms. So this means that it's not worth it to go for higher density ensembles, as the dipolar interaction within these ensembles is going to affect detrimentally to the signal. While for the other two options of the SHIELD protocol, we achieve actually a higher signal-to-noise ratio than the best achievable with the CPMG protocol. So to finish the talk, let me make some conclusions. So we checked that even at pretty standard MV concentrations at 0.4 ppms, the dipolar interaction detrimentally affects the outcome. So this being the situation, the scenario, we designed a protocol, SHIELD, which cancels these detrimental interactions, which what allows to measure with dense MV ensembles with an enhanced signal-to-noise ratio. It is also robust against other kind of errors, like errors in the microwave or magnetic noises in the surrounding. And importantly, it is compatible with high-field NMR. And all these three properties work together to offer a system with an improved sensitivity. And before finishing the talk, I would like to say that we are actually working on the implementation of this protocol with a collaboration with Professor Fedor Jelesko's lab. And apart from that, there are new projects going in the same direction. Actually, Jaime Olivares, who is another member of the group, is also working in another project that uses similar decoupling mechanisms, but in this case to decouple the MV from the fast noises coming from the spin bath. And thank you. This was everything, and I hope you enjoyed the talk. And if you have any question, I will be pleased to answer.
Any questions for Ainitze?
Thanks for the very nice talk. I was wondering, Ruben, if I understood correctly before, he said that in the same diamond there can be MV centers pointing in different directions, in 4, I think, different directions. Did you consider this? I would assume that the direction affects the type of dipole-dipole interaction, and if it does or so, did you consider this, or do you have?
Thank you for the interesting question. Yes. Well, you are right. The coupling is different when the coupling is between two MVs that are in the same direction and in the different direction. The thing is that the most problematic coupling is that between MVs that are aligned, which is the homonuclear dipolar coupling. The coupling with the other MVs is exactly the same as the coupling with other paramagnetic impurity, which is just a set-set type of coupling. And these couplings are suppressed with the pi pulses. Thank you.
Okay. Any more questions for Ainitze?
Are the pulses that you're using also suppressing the noise coming from the nuclear spins in your? I mean, so these CPMG or the additional ones that you apply, do they also take care of nuclear spin noise?
Yes, it's the similar question. Well, the coupling with other nuclears is also set type coupling, and you get to you get protection against this coupling with the pi pulses, as you rotate the MVs but not the nuclei.
Okay, so thanks Ainitze again. Thanks for the talk.